I'd like to make a quick few comments about the energy balance approach to estimating ET. So remember how it works. This is a little cross section of the Earth with some trees or some vegetation here, and the idea is that we're simply going to draw a box around this here. I'm going to draw a box around this. Let's try to do a better box than that. We're going to draw a box around some part of the Earth, and we're going to keep track of energy in and energy out and use the energy balance equation, which is equivalent to the mass balance equation, to compute. So we're going to find, we're going to measure energies in, right? Energy in, measure energy out. And what we're going to find is that the energy in is going to exceed the energy out. So where does that energy go? Where does that excess energy go? Well, the reason there's more energy in than out is because some of that energy in goes into evaporation. Because remember the reaction of water, liquid. If I want to transform that into water vapor, I need to add energy. And this becomes H2O vapor. So the energy added to convert liquid water into water vapor, this is the latent heat of evaporation. And in order to heat of evaporation, right? And so this process here, this is ET. And so I am essentially estimating ET by the amount of energy that was used to evaporate the water into water vapor. So I'm going to find out that there's a certain sort of energy loss in here. That loss, it's not been lost, it's been used to convert the water into water vapor, and then it's sort of escaped via water vapor leaving. We're not going to worry about that. So the idea is I keep track of inputs and outputs, and the energy deficit then is assumed to be due to the latent heat of evaporation, and it is therefore an indirect measure of the amount of evapotranspiration. Now, there's a couple. Probably the most difficult thing to understand here is the way we have to estimate these energy flows in or out. And some of them are pretty easy, right? We have for example, energy from the sun coming in, and that's pretty straightforward. We have energy emitted by the Earth. That's pretty straightforward. We pretty much ignore any kind of horizontal energy in and out usually, and we usually also we ignore any kind of conductive heat produced by conduction from the Earth into the atmosphere above. But the big one, the big term that's very important, that really is the most important here, is the energy lost by transfer processes from within my box out of my box. And we can write that using a diffusion type equation, right? So this is the energy loss let's give it a different color so it's really clear what I'm talking about here. So it's this transfer of heat up by mass transfer processes that I'm calling J here in orange. It's that orange arrow. And I can write that transfer of heat is described by a diffusion type equation. Remember, that's simply minus some coefficient. I'm just going to call that C asterisk for reasons that I'll explain in a minute, times the gradient of temperature. That's a term from calculus. We're not going to use calculus. Remember, we're just describing it, right? And that, in this simple one-dimensional case, is equal to simply the change in temperature divided by some change in distance. So in other words, what I'm looking for is the difference in temperature measured between two vertical points. And so I might pick a point right here, for example, and a point on the surface, right? And so this would be that this distance here is the change in elevation, delta Z. And in order to use this equation, this equation to calculate the heat flow J, I would need to know then the temperature at this elevation here. I'll just call it T sub Z. And the temperature at the surface, I'll just call that T sub 0. So that I can write this, so this will equal now minus C star times the change in temperature. Well, that's just T at whatever elevation I'm at minus the temperature on the surface divided by this distance delta Z. This might be, to put numbers on it, this might be 2 meters. That's a pretty common one, right? So in other words, I'd measure the temperature 2 meters up off the ground. I'd measure the temperature on the ground, and then this would then, in that case, this would equal whatever that coefficient is times the temperature at 2 meters minus the temperature at the surface, whatever that temperature difference is, divided by 2 meters. That would be an estimate of the heat flow. So the stronger that temperature difference is, the more heat flow is going to move upwards and out of my little box. Now the complication, and the reason this gets quite hairy, is that this coefficient is not actually a constant. This thing here is not a constant. Not a constant. In fact, it is, in a complicated way, it depends on the gradient. Remember that, there it is, the gradient of the wind speed, the velocity of the wind. Okay. In other words, if there is a difference in the wind speed, that will aid the transfer of heat upwards by the process of actually these turbulent convective cells. So in other words, if the wind is completely still, then wind doesn't play a factor. But if there's variations in the wind, and there almost is, because the wind, we'll talk about in a second, we always assume that due to friction, the wind at the surface is essentially zero. And so as we go aloft, if the wind increases, that will increase the transfer of air and carrying heat out of our box. So in order to actually use this equation, we actually need to know something about the gradient in wind. So let me slide up here a little bit so that I can make some space for myself here. So remember, the gradient, again, we're talking about the vertical gradient in the wind speed, and that's just equal to the change in the wind velocity divided by the vertical distance again. So it's the same exact thing I had before, right? So this will equal the velocity of the wind at, say, some elevation z, minus the velocity of the wind at the surface. I'm just using z to mean the surface, divided by the change, this height z, whatever that distance is. And once again, if I want to provide a specific example, if, for example, if I let this distance here equals 2 meters, again, that's a pretty common one, then I could say that the gradient of the wind speed will equal the velocity, whatever the velocity of the wind is at 2 meters, minus the velocity on the surface. And once again, very commonly, I will assume that's 0 divided by 2 meters. And so that's why it's really easy, right? So it's just going to be the velocity of the wind at 2 meters divided by 2. And that would be my velocity gradient of the wind in that particular example where I'm measuring it at 2 meters elevation. So the trick is now that I've got to actually know a bunch of things, right? Well, I'll just circle them in. I'll circle them in pink here. The things I need to know to use this simple expression here for calculating the heat flow carried out the top of my little box here. I need to know the temperature at some elevation like 2 meters. I need to know the temperature at the surface. I need to know, obviously, this distance. I need to know how far I was at, what elevation I was measuring the temperature. But in addition, I need to know the velocity of the wind at that same elevation as well. I don't need to know the velocity of the wind at the surface. I'm assuming that's 0. So I need to know the velocity of the wind at, say, 2 meters. I need to know the temperature at 2 meters, and I need to know the temperature at the surface. And that's a lot of information that I often don't have. But in order to actually use this equation rigorously, I need to know all that stuff. And then I can go on to calculate the energy, do the energy balance equation and find out that there's a small energy deficit, which I will then attribute to the latent heat of evaporation and the process of evapotranspiration, and compute the amount of evapotranspiration that must have occurred.